Okay, so we the last talk of the session will be of Kaveh Eftekharinasab. I hope I pronounced
Yeah, Eftekharinasab, yeah.
yeah, of Kaveh. The talk will be 40 minutes according to the time slot. I would like to say a very few words about Kaveh. Kaveh is a senior researcher at the Institute of Mathematics of the National Academy of Sciences of Ukraine. His main interests are in analysis and geometry of finite dimensional manifolds, especially the Frechet manifolds. His talk will focus on spray geometry in infinite dimensional setting, and the title of the talk is Spray-invariant set in infinite dimensional manifolds. Yes, Kaveh, please, you can.
Thank you very much, Mira. Well, the talk is, I will, it is based on the very recent, some days ago, I finished the paper, now it is on archive. And it is going on. I haven't working on the problems yet. So a very fundamental question is to characterize subsets under how we can characterize a subset under the flow of when subsets are invariant under the flow of vector fields. This is a very general question that I have been working on this problem, and I was looking for the application that comes to idea to study geodesic preservation. So it is a completely something new that is based on the what is called the flow invariance subset. So I try to adapt that notations of flow invariance subset to for the studying geodesic preservation. So for subsets of infinite dimensional, the aim is to study subsets characterized by this property that any geodesic of a spray that originates in the set, it will remain in the set for its entire domain of the definition. So such sets which are called spray-invariant are possibly singular, especially stratified spaces, which are very common in infinite dimensional manifolds, the infinite dimensional settings. And as you see, we will have many examples even in simple settings such as linear spaces with flat sprays. And also, there are big differences between differentiable submanifold and non-differentiable. For example, non-differentiable submanifold, they show sensitive dependence on parameterization of the geodesic. So if we reparameterize the geodesic, then the invariance may change. It affects the invariance, which is not the case for differentiable submanifold. So what is the spray? There is a very elementary result in linear algebra that any symmetric bilinear form can be recovered fully using the quadratic form via polarization. So there is a fascinating lift of this result to differential geometry. It was proved by Ambrose, Palais, and Singer in 1960 that there is a natural bijective correspondence between symmetric affine connections and sprays. Here is symmetric affine connections. They are analogous of symmetric bilinear form, and the sprays are analog of quadratic form. The sprays are vector fields on the tangent bundle that describe the second order differential equation of Hasse. It provides machinery to define geodesics intrinsically. Without need to any metric on any Finzer structure. So once we have a spray, from this spray, we can define connection, we can define exponential map and quadratic covariant derivatives and the whole geometry without length. So why it is proper what is appropriate in infinite dimensional case in our situation? We are interested in the dynamic of the geodesic. So without inducing any length for the geodesic. Now here there are significant differences between finite dimensional geometry and infinite. For example, Hilbert manifolds and small classes of Banach manifold, they admit only Riemannian metrics. The other class, well, most of the interesting examples of infinite dimension, they only admit weak Riemannian manifold. So weak Riemannian manifold, weak Riemannian metric, it's not in general induce Levich-Vita covariant derivative, and also it induces in general the pseudo metric. That is, the two distinct points can have a zero length. And also the Finzer geometry in finite dimensional Finzer metrics, they are smooth on tangent bundle away from the zero section. But for infinite dimensional setting, we need to give up the smoothness because it is too restrictive for many infinite dimensional examples. And Finzer structures, they are just merely continuous on tangent bundles in infinite dimension. So it has a consequences that we don't have a canonical spray which is induced by the Finzer metric or Riemannian metric. But for our problem here, we don't need any the existence of spray which is induced by Finzer or Riemannian metric or comparator with them. So for us, the spray geometry, it is a appropriate framework to work here. So regarding the differentiability, there are various notions of differentiability for locally convex spaces. The one which we use is Mitchell-Bastiani. It is commonly used for locally convex manifold. Here is the definition that mapping is called, it is differentiable if all the directional derivative is exists. And also it is continuously differentiable, C1, if the derivative is jointly continuous. Here we don't consider the derivative as the element of the space of linear continuous mappings between E and F, which is very probabilistic, this space. So that's a very natural definition without using any topology on the space of linear continuous mapping. There are a lot of things to say about it, but well, I will skip those arguments. All right, so that's our notion of differentiability that we use, and our manifold we require to manifold be to at least of class CK4 because the spray R will be the class of C. We need to have the class of C2. So now, what is the formal definition of the spray? This work for all finite dimension, infinite dimensional manifold. Here, if M is a manifold modeled on F, and the tau is the tangent bundle, and tau sub 2 is the second double tangent bundle, a mapping on TM to TTM is second order vector field if its composition with the push forward of tau is the identity, and if in addition we have the composition of V with the tau sub 2 turns the identity, which we call it the symmetric second order vector field. Now, spray is a second order symmetric vector field which satisfies this homogeneity condition. Well, for any S and V, as a real number S and V, the L is the scalar multiplication on the tangent bundle, and the spray evaluated at the scale vector SV is equal to the differential of L applied to the S times S of V. That's the homogeneous condition. To see it, to visualize it locally, consider the this chart, and the spray completely can be described using this function, which is too homogeneous. Spray has a pretty easier local representation rather than the other structures like Finzel structures for infinite dimensional manifold. So working with the spray is much easier than Finzel structure. So I know what is the geodesic. A geodesic of manifold. A geodesic is a curve on the manifold if its canonical lifting G prime is the integral curve of S. So it means that the acceleration is equal to the spray acting on the canonical lift G prime. So any geodesic, in order to geodesic to G to be geodesic, it must satisfy the second order differential equation. If S is comes from Riemannian or Finzel metric, we can talk about the length of the geodesic. So actually, this is the intrinsic definition of the geodesic. So without needing to the length or the Riemannian metric of Finzel metric. All right. Now to handle non-smooth submanifold, we need the concept of adjacent cones. Also, this definition satisfies valid for all the infinite dimensional manifold, but we look at it for the Frisch-Limit for generality. So if we have the Frisch space F with the semi-norms, well, these semi-norms define the pseudo distances. If S is a subset as a point, a vector in the tangent space of at S is called the first order adjacent tangent vector to S at S if there is there is a chart around S that for all semi-norms such limit conditions satisfied, the set of all of these vectors is the tangent adjacent tangent closed. So this limit condition, it well, intuitively it says that if we approach S in direction of V, all the pseudo distances from the line points on the line S plus Ty to the S approaches to 0 when T approaches to 0. And also, well, we define the second order adjacent tangent. And if S is the smooth or differentiable submanifold, it is a just tangent vector. So the second order adjacent tangent vector is that if V is belongs to this tangent, this adjacent cone at S, and W is the element of T double sub tangent bundle at V, then it is called the second order adjacent tangent vector to S at S associated with V if there is a chart and we have this crucial conditions that relates V to W and it satisfies these limit conditions for L. Here the interpretation is like the, well, similar, but we have the higher level. All right, so our first crucial structure is this subset of the tangent bundle, that if we have a spray S and we have the subset S, a tangent vector V is called admissible for if the projection belongs to S and if S acting on the V is the second order adjacent vector to S at the base point. And the collection of it, we call it the admission. And then we prove that a geodesic belongs to the S for entire domain of the definition if and only if its canonical leaf G prime of T belongs to this admissible set. So here it gives us this idea that this admissible set, it captures right initial conditions to for a geodesic to remain in a subset. So it leads to this definition that we call a subset spray-invariant if any geodesic of M with these initial conditions that G of T belongs to the set and G, the tangent vector, belongs to this set, then G of T belongs to S for all the entire domain of the definition. So this definition is generalized the totally geodesic submanifold. And it includes also singular spaces. And as we can see, there are totally geodesic submanifolds. They are spray-invariant, but we have the spray-invariant sets which are not totally geodesic, as we will see. So our first example is the space of smooth real valued function, and we consider a simple flat spray. Here the oscillation is the zero vector, and the geodesic are just affine paths. Now we define the set S, which is the union of two subsets, S plus, which is the all functions with non-negative support, and S minus, all functions with non-positive support. Both of them are a smooth manifold and closed, but the union is singular at zero. There is no neighborhood of the zero function, which is homeomorphic to any Arino sphere. Well, and we compute the admissible set, and well, it is easy to verify that the geodesic with these initial conditions will remain in the set, because the derivative is equal to just V, and V is belongs to this set, to admit the Schwarz. So that's straightforward from the definition. All right, so as you can see, we have, well, in linear case and with a flat spray, we face such spaces, such a spray-invariant spaces. Now, a question that arises is that what if we reparameterize the geodesic? What will happen? So here is the notion of projective invariant. Two sprays are called projective invariant if any geodesic of one of them after the parameterization will be the geodesic of the other, and vice versa. And we observe that if S is not a differentiable submanifold, those admissible sets can be different. Now, here, look at the example that we have. We have this singular set, which is spray invariant with the flat spray. Now we try to modify this spray and get another projective equivalent spray. So here we just modified the second derivative by multiplied of adjacent vector with this acceleration function. This acceleration function is constructed by using the standard bump function. And we can check that for this new spray, which now the geodesic are not straight line, not affine passes, then this S is not spray invariant. And also we have the close relation between this set and totally geodesic. Here is the characterization that if the submanifold is sufficiently smooth, then it is totally geodesic if the admissible set is entire the tangent bundle. So intuitively, it is not hard to prove this one, but intuitively you can see that what is the totally geodesic? Totally geodesic, all the initial conditions on tangent vector must belong to the tangent vector. But if T is the admissible set, then well, we get all the all the vector or the initial conditions for the set to be invariant, well, under the spraying. And this theorem has a corollary, which gives the practical way to check the totally geodesic submanifold. It was proved by Serge Lang for Banach manifold using the different technique. So the discovery is that if M is 2, there is a unique geodesic that pass these two distinct points, and S is a closed C3 submanifold with the property that any two distinct points can be, there is a unique geodesic between them. If this sonic condition is satisfied, then this is totally geodesic submanifold M. So we have some examples, illustrative example. Well, consider the space of R smooth map from R to R squared, again with the flat esprit, and define this subset of all functions of this form. Here H is the smooth function from R to R. So we can prove that S is the smooth Frichet submanifold of M, and we compute the admissible set. So this means, as you can see, the admissible set, it means that in all initial conditions where the tangent vector is 0, only admissible. And here the geodesics, are just the function f. So belong to the S. That is, it is the Spray-invariant. And if we compute the tangent bundle, this is the tangent bundle. As you see, they are different, they are not equal, and so by that theorem is not totally geodesic. And also we can show it directly that it is not totally geodesic. Another example is the all real valued function from Rn to R with the flat esprit, and we have the space of all constant functions. On Rn is the closed linear subspace of R. It is a smooth submanifold, and well, it is not hard to do all the conditions of the corollary, so it is the totally geodesic submanifold. All right. Now, an interesting question is that when the diffeomorphism of manifold preserve the flow spray invariance. So here we define this automorphism of a spray, that if phi is the automorphism, then this combination is, we can show it is also the automorphism. If it is equal to S, we call it the automorphism of the spray. And so it is the group under the composition, and we proved that if S is the non-empty closed subset and spray invariant, then this automorphism of a spray, also f of S, will be spray invariant. So it provides us the new spray invariant subsets. Here is the illustrative example that what we had, that singular invariant spray invariant set S that we had. So we consider this intuitive common used translation math, which just lift horizontally the graph of the function. So it is well, we can show it is automorphism of the flat spray, and it translates the geodesics affine geoclasses to affine classes, and so the spray f of S under the application of phi will be also a spray invariant. So I was trying to study this structure in case when M is smooth compact manifold and it is a smooth spray. What is the structure of this one? Here, well, it is a little bit hard question because we don't have the closed. So that's a very important closed submanifold theorem for Fréchet case. So that's to study the structure of this group. It requires pretty hard partial differential equations that are elliptic differential equations that I'm not very real familiar with them. So that's a and also here is the closed submanifold theorem, which is open for Fréchet manifold. So that's a question that I will try to work on that. And now a key question is that so if S is the spray invariant, and the spray, if we look at it as a first order vector on the tangent body. So the question is, does the spray remain second order adjacent tangent to this admissible set? So it helps us to reduce the problem of second order dynamics on M to the first order dynamics on the tangent body. So which one is more tractable? Here, to address this question, we have this powerful theorem of Nagomo-Brezis that provides a criteria to determine the invariance of set under the flow of the vector field. So this theorem is available for any Banach manifold, but for Fréchet manifold, just for a result that I proved just recently for a special category of Fréchet manifold under the nuclearity assumption. So we have a lot of strong definition of differentiability in 26 by Olaf Murray. He was trying to prove the inverse function mapping theorem for Fréchet spaces without the need for tameness. So to define this differentiability, he uses the special translation in one matrix that defines the topology of the spaces. And now the space of linear globally Lipschitz schematic continuous mappings, we can define translation in one arithmetic while using the Lipschitz constant. Now, a mapping phi is if it is in the C1 mapping in the sense of Michel Bastiani, and it is called bounded or MC1 if the directional derivative belongs to this space, and the derivative is the continuous as operator from U to the space L of E, which is endowed with that metric. Unfortunately, this is a strong condition, and well, it is hard to verify it in practice. And the class of these functions can be quite small. And also, the nuclear space was defined by Grothendieck that if we have two Banach spaces, the operator is nuclear if it is of this form, and the nuclear space is locally convex vector space such that any continuous linear map to Banach space is nuclear. So Banach space cannot be nuclear. Nuclear space have very good properties like a Heisenberg property, and seminorms are Hilbertian, they are semi-inner products. So, and now we have this definition of flow invariant, right flow invariant. If we have A and vector field on M, then it is called flow invariant with respect to if for any integral curve of F with the initial point, that is the initial point in N, then IIT will remain an N for T more than T0. And well, the theorem of Nagomo-Brezis that I proved, and actually I was trying to find applications for this theorem that come with the idea of that I'm talking about. That was the main motivation for me, was to try to use this formula, this theorem. Now, if is a vector field and A is subset is closed, then A is flow invariant with respect to V if and only if for each x we have a chart such that this limit condition is satisfied. And it is, well, it means that V of x is just an adjacent tangent vector to this set at phi of x. So using this theorem, we can give another criteria to determine spray invariant. And if M is nuclear reflection manifold and S is the subset such that the admissible set is closed, then S is a spray invariant if and only if S is the adjacent tangent to the admissible set when it is regarded as a vector field on Tn. Well, we have this theorem for arbitrary Banach manifolds. There is no need for nuclearity and just a CK Banach manifold, and it provides us another way to check if the set is a spray invariant. So I will maybe briefly give an example here. We have the Banach manifold of K times differentiable on the circle with the flat spray, and this set of non-negative functions. Well, it is a convex cone at the vertex or at the zero or the zero function. So it is not hard to show that this spray is adjacent to the admissible set, so it is the spray invariant. That's another way to check it. Also, we could choose it directly by the definition. Another criteria, well, based on the transversality, is if M is the nuclear MC coefficient manifold and S is closed, then S is, if we restrict S to the tangent bundle, and if we have this transversality condition that S of T of S restricted is transversal to the T of S, and then S is spray invariant with respect to S if and only if this differential condition satisfied. Unfortunately, this transversality condition is very strong. In even simple settings, it is not satisfied. When I haven't, even for Banach or Hilbert manifold, I haven't found any examples that satisfy. Or I have, well, even in simple settings, this condition is not satisfied and hard to check in practice. So it makes it less practical. And well, how many times do I have? Maybe, well. And also, another thing is that, well, we can use is the geodesic flow. Geodesic flow is, for Fresher manifold, it may not be exist or well defined, but for the Banach manifold, we have this concept of the geodesic flow. The geodesic flow is mapping on tangent bundle. It describes the evolution of the tangent vector along the geodesics. So what we expect is what this theorem that a closed subset is spray invariant if and only if its admissible set is invariant under the geodesic flow. It also provides another way to check if the subset is spray invariant. So let us see, have a more interesting problem, a more example of Hilbert manifold of the space of square integrable maps from circle to the two-sphere. So this Hilbert manifold, it admits the L2 Riemannian metric, and it has the canonical spray, the geodesic of the matrix, or the geodesic of the canonical spray. Now we define this set C, which is the great circle. It is the total geodesic submanifold of S. And now define this closed subset that all functions of M such that they are almost constant for all theta on the S1 or the circle. So we can show it is not, well, it requires a little bit of work that the admissible set for is invariant under the geodesic for, so by the theorem it is Spray-invariant. Another example is the separable Hilbert space of the square summable real sequences, but with a standard inner product. And now we consider the space of S. The space, which is the space of all finite sequences, when we can represent it as the countable union of this finite dimensional linear subset HA, which is spanned by the standard orthonormal basis of H. Well, so again, consider the flat spray of on this space, and for any x, yes, and with these initial conditions, we can find K that the geodesic belongs to the K, and so as H of K is the linear subspace, then the geodesic belongs to the S. So S is the Spray-invariant. However, S here is the stratified space. Well, we can define this stratification of S into such strata. And the frontier axiom, well, not hard to show it that's satisfied. So this is one example that we have the stratified Spray-invariant set. Now, the last thing that I think I have is just a couple of minutes to say. The last thing is that we'll try to study the action of smoothly grouped on manifolds. So if G is a smoothly grouped that acts smoothly on a smooth Banach manifold F, a spray S is called the G invariant if, and for any G, we have this commutative diagram. And well, we define the isotropy or stabilizer group as the usual. Now, the last theorem. The last theorem is that, well, the question is that if G is finite dimensional smoothly grouped that acts smoothly on a smooth Banach manifold, and we have the smooth G invariant manifold spray. Now the question is that we are interested to obtain the orbit type decomposition of B. Here, this assumption that relies on the existence of a nice slice at a point. We have this assumption that gives us the answer, but however, this assumption is not necessary. It is more just a sufficient. I found an example that without this assumption, we have the orbit time decomposition. So this assumption is that if for any x, any point of the B, there is the G equivalent neighborhood U of X and the G equivalent diffeomorphism. And here V is the appropriate slice that I will define it shortly. Then we have this orbit type decomposition of B, which defines the stratification of B, and each stratum is a Spray-invariant. All right, so what is the slide here? Slice is roughly speaking, it is just well-behaved submanifold, which is the transverse to the orbitatics. And locally, the manifold, it's look like the product of the orbit and these slides. And here, these these conditions that are listed here, they are just requirement to prove the theorem. I don't know if, well, especially this condition could be hard to verify, and especially the transversality condition. And it could maybe relax these conditions. But here, these conditions are just merely to prove the theorem. So maybe it is not the best possible definition of the slice or assumption that maybe we can have a slight here relaxed assumption. All right, so and also the last thing, I think I'm just in time that, well, this theorem, it says that the geodesics, well, here orbit type strontium are spray invariant. It does not imply that geodesics remain in the same interval orbit. Well, I think I just finished at the time. Thank you very much.
Kaveh, thank you very much for an amazing talk. Thank you very much.